Right, so there's the scale-up network, which is really closely coupled, and the scale-out. And so I think the scale-out is where Ethernet fits in.
Makes sense.
So then the question becomes, like, which of the semantics that InfiniBand provides do we actually need? I mean, as you guys well know, right, we've seen lots of technology, technology A replaces technology B.
Oh, yeah.
A wants to do everything that B used to do plus better. Then after a while, you figure out what it doesn't need to do anymore.
Welcome to the Cables to Clouds podcast, your one-stop shop for all things hybrid and multi-cloud networking. Now, here are your hosts, Tim, Chris, and Alex.
Hello, and welcome back to the Cables to Clouds podcast. I'm your host this week, Tim McConaughey, at Juan Golbez on Twitter. And with me, as always, is my lovely co-host, Chris Miles, at BGP Main on Twitter. And with us is a returning guest, Peter Jones. Is it Peter at Peter G Jones on Twitter? I don't remember.
It is.
I
have Peter G Jones in a whole bunch of places.
That's right. I thought so, but I didn't want to speak and be wrong. But so Peter's a returning guest. I'll let him introduce himself, but actually, let's do that first. Go ahead and introduce yourself, Peter, and then we'll get into it.
Okay, so I'll try and be brief. When I do this at Cisco Live, I get my co-speaker to introduce me. It's always more fun.
Oh, well.
So I'm Peter Jones. I work for Cisco as a distinguished engineer in the hardware networking business. I also do a bunch of work in IEEE 802.3 standards. I'm mostly on low-speed ones, and I chair the Ethernet Alliance. Now, strictly, be very clear, in this meeting, I'm speaking for myself, not for anyone else. And as I said to these guys earlier, I have a lot of opinions and some of them are good.
That's what we like to hear. But yes, so Peter actually is a returning guest. This was actually, I went back and looked, Chris. This is actually one of our, I won't say first shows, but it's pretty early in our run. We had Peter on a year ago, back in August, and at that time we wanted to know Peter's opinion on because AI was really starting to take off at that point. We wanted to know Peter's opinion about, like, okay, well, now that everybody's building these AI-powered workloads and everything, what is building networking for them going to look like? And at the time, of course, it was still way too early to make any kind of predictions. Exactly. I think you did something very similar at the time, or maybe you asked something like, would you like me to just pull something out of my ass or something? But
I would never have said anything like that. Maybe.
But yeah, right. But now it's been a year. And I mean, anybody who's been paying any amount of attention knows that there is a lot and it is moving insanely fast. And so we thought it'd be a great idea to bring Peter back and do a little bit of a retrospective, just a little bit of like, hey, how has it been this last year? Did it meet any expectations that anyone had? And then looking forward, like what's on the horizon, especially in terms of what AI networking is going to look like moving forward, we think. So yeah, let's start right there. So it's been a year. Again, we had no idea what it was going to look like a year ago. I feel like it's changed and been so different for this past year. Peter, so what's been your observation for how this has gone?
If you think for the time being that right now NVIDIA is being the best supplier of picks, shovels, and wheelbarrows in the world,
yeah,
and we know that our web-scaler colleagues are buying everything they can sell as fast as they can buy it. So we know that if you want to get interest in Wall Street, it's like you must mention AI in everything. So it's clearly flavor of the year. Now, I've been looking at some numbers. There's an enormous amount of capital going into building data centers.
Oh, my God.
And doing a little bit of research recently, I've got myself a lot smarter. And these guys are a lot further advanced than I imagined because I just wasn't looking. What's interesting is if you look, there's actually a whole bunch of stuff out there about how this stuff's being built. And maybe there'll be some links we can put in the show notes to help people go take a look themselves.
For sure.
Yeah, I think probably an important thing to level set here is, it's been a year since we've had this conversation. I think even back when we had the original convo, we probably didn't even have this. Hang on a second, there's a plane going over. But I think when we had this conversation a year ago, this was before we even had kind of the differentiation in our minds about AI for networking versus networking for AI. So like today, the premise of the show is about networking for AI, right? And how to build networks for the purpose of, training models and doing RAG and things like that. And even some more very complex stuff that I'm probably not smart enough to understand. But
all that stuff that the people with billions of dollars in their budgets are doing.
Exactly.
So this is actually the don't try this at home because you can't.
Yeah, good luck getting your hands on any of this gear.
I'll put the little jackass disclaimer on the screen. Don't try this at home.
So one of the things that really got to me was when I read that Microsoft was paying to reopen 3 Mile Island, and it agreed to pay for all of its power for 20 years. You go, okay,
that's crazy.
It's just like this is All right, so if we go back. So this has been rolling around the networking business I live in for a while. Everyone's been going, well, we should do AI for networking for AI, and it should be this, and it should be that, and it should be all the other things. And as you know, I put a while ago, I put a post up about the 9 blind men and the elephant. So no one exactly knew what it was. So there's a whole lot of stuff came out of OCP, which was a week and a bit ago. All those slides and videos are online. I'd highly recommend people go look at them, because I'm going to only scratch the surface, if that. So I think the big thing that people have figured out is if you look at the structure of a network, they tend to speak about back end and front end. The front end is our normal network, and the back end is a network specifically for AI. Then they talk about scale out versus scale up. So scale up is basically the communications between a very closely coupled set of GPUs and CPUs. And that set could be anywhere from tens to hundreds to thousands, depending on who you are. Then there's a communication between those clusters, which today is mostly part of a data center, can become a full data center, multiple buildings, and then you start going into multiple data centers in a region. So there's a whole bunch of stuff about Google going off to try and train stuff across multiple data centers. And as you all guys know, right, when you go from place X to place Y, things get really interesting because all your assumptions tend to break.
Yeah.
And so the Ethernet Alliance event we had last week, which was called Ethernet in the Age of AI. Unfortunately, it wasn't recorded because we were trying to preserve the ability to have a whole lot of conversations which would be interesting. Right. It was triggered by a friend of mine being, talked to by someone else from Meta. And the argument was, well, this Ethernet with 200 gigabits per lane is almost done. What about 400 gigabits per lane? And he was like, we're just starting to write the baseline for 200. What do you mean it's almost done? And I think the thing here is that the expectation is just so high. If you look at it, as much as we think networks are important, they're just a means to an end. In a campus, the network exists to let other people do their job.
Absolutely.
In these places, the network exists to let GPUs do their job. And so, in an ideal world, you don't notice the network when it's not there.
That's right. So, infrastructure, right? Good old water power.
And so the thing that's a little different about some of these workloads is that they do, and there's a whole lot of complicated stuff I had to read about all-to-all and all-to-this and transformers and stuff. But in general, there's these massively parallel workloads that every now and again have to stop and talk to each other. And the problem they tend to have is until they've talked to each other and finished, they can't go forward. So they have a barrier to going forward. So what they really care about is in that network, while you're busy, you've got to be 100% busy. So this is where we're seeing a whole lot of stuff coming out about how to do load balancing more effectively. And there's a bunch of ideas out there, but it seems to be the conclusion seems to be in the Ethernet side of the house. What you have to do is you have to spray across all the links. You have to reorder them the way out of the network. So the sort of general assumption is, so for that period you're busy, and I don't really know whether it's 10% of the time or 5% of the time, you want to be 100% full.
Right.
You want no congestion and you want no packets dropped. So the run-of-the-mill story is if you build it as non-blocking and if you load balance evenly across all your links and you reorder on the far end, you're okay. There's a bit of a disagreement about whether you reorder in the exit switch or in the NIC.
Yeah.
I tend to think it's the NIC because the NIC can be connected to multiple switches.
That makes sense.
Now, there's also a whole bunch of questions about why does latency matter? And my judgment of what I heard last week is latency matters a lot in the scale-up network, which is within the relatively small set of GPUs. And they're running something like NVLink. There's another group that started up recently called UA-Link. So this is the Universal Adapter something or other link. So this is basically the everyone but NVIDIA coming up with an alternative to NVLink.
Got it.
So these extremely high bandwidth, extremely low latency, extremely reliable. This is basically giving you semantics like you are inside a system. But those links only go so far. The exception to that is Google, who has a whole bunch of interesting stuff on their network called Jupiter, where they use a whole bunch of programmable optical switches. And so their structure is a little bit different. I think in sort of the meta of Microsoft, their idea of a scale up is like maybe 10 to 100 nodes. Google is more like some number of thousands.
Oof. Okay.
And they're also using the fact that they have this optical cross-connect to simplify adding or deleting from the network because they don't recable anything.
Yeah. I'm having trouble visualizing it. I'm just thinking through it. I'm having trouble visualizing what that looks like ultimately.
Right, so there's the scale-up network, which is really closely coupled, and the scale-out. And so I think the scale-out is where Ethernet fits in.
Makes sense.
So then the question becomes, like, which of the semantics that InfiniBand provides do we actually need? I mean, as you guys well know, right, we've seen lots of technology, technology A replaces technology B.
Oh, yeah.
A wants to do everything that B used to do plus better. Then after a while, you figure out what it doesn't need to do anymore.
Right, you pair it back, right?
I've been through, Sonnet and X25 and ISDN, et cetera, et cetera, et cetera. So now if you look at some of the things that UEC, the Ultra Ethernet Consortium, is trying to do, so they include link level reliability. So this is guaranteeing a packet gets from one end of the link to the other and retransmitting if need be. So because they're trying to provide a reliable network semantic like InfiniBand does. Do you need this?
Just real quick before I forget, Peter. So link level reliability is not, we're not talking about like, so normally we do this with like reliable protocols, like for example, TCP or whatever. What is link level reliability? What is the mechanism?
That means you basically acknowledge individual packets across the link and retransmit if I don't get there.
Like at the switch or the whatever the device level is.
If you go back in time, way back in time, added 2.2, which is LLC, defined type 1 and type 2. Type 2 was reliable.
Yeah.
Okay, gotcha. I'm following.
And the sort of the interesting assumptions in here is that the places, they're trying to avoid any queuing delay. So InfiniBand offers you lossless semantics, and so they're trying to match that.
Okay.
I'm not convinced whether you have to do that or not. I think that one thing we tend to forget about, I mentioned in warm-up, right, we were talking about the 12 networking truths, RFC 1925.
Yep.
And rule 6, which is it's easier to move a problem around the network than it is to solve it. And sort of the corollary of that is it's easier to assume you know what the other guy wants and work inside it.
That's right.
And I think in reality, there's much more conversation to be had about how to write software that interacts with what network hardware can actually do. Because we can make network hardware do some really strange things, but may not be the best idea. Part of the problem we tend to have is the communication between the web scalers at the front and some of the networking people is a little bit sparser than it should be.
Yeah, this may be a bit of a silly question here, but I'm just kind of thinking in context about, networking for the longest time has been solving applications problems, right? We've been solving the problem of, bad code writing for years and years. And, we've seen things kind of
order packets.
Yeah,
out of order packets, lost packets.
We've seen things moving down the stack. Like if you think about like the Quick protocol, that was kind of solving some of the stuff with some stateful nature of TCP, and then TCP's supposed to be able to handle reordering packets and things like that. So it seems like, in my mind, we're moving that even further down the stack, and we want that reliability built into the link layer. And I guess my bare bones question is why do we need to do that at the link layer just so TCP doesn't have to do that at the up the stack?
So
is that the whole point?
I'd say this stuff is not running TCP.
Yeah.
But I'd also say that the competitive technology does this.
Okay, so therefore you just assume that you need to do it.
The easiest way to come in is to say, yes, I do that.
Yep. Yeah, you're absolutely right.
And so we've been through this with data center networking, building networks for Rocky, etc. the easiest thing to say is, yes, I do everything that did.
And
now
more.
the question, and cheaper. So the question of last week the conversation I was trying to get to was what we should do, not what we could do, because we can do lots of stuff. And so some of the things that all came out of it was like, everyone has a different opinion of this thing, right? This is the man and the elephant. And, I can always find someone who wants what I want, right? But it's very different to figure out what's the right thing across the industry, and that's really hard.
Yeah.
I mentioned earlier that, scale up and scale out are really, really different. So we started talking, if you're talking copper versus optics, it all comes down to cost, power, and reliability and reach. Optics is great for reach, but cost, power, and reliability stick.
Absolutely.
And in these networks, right, there's so many devices that you have, if your error rates end up that you're getting errors in the numbers of minutes, right, because there are so many links in these networks. So in some points of view, the networks are having to be designed to account for errors that we don't normally see.
Okay. Yeah, this is a little bit in the reverse order of, when you migrate an application, some homegrown application, you take it out of the data center, put it in the cloud, and add 50 milliseconds of latency. All of a sudden, the app doesn't work anymore. This is like the opposite of that, basically.
So, people are looking at you can get really frequent adapter failures or copper failures, and you go, yeah, that's not such a great thing. So again, there's discussion about how big can you make a radix of a switch. So my friend from Google said he actually likes lots of small links, and he can make the radix bigger and have less levels in his network. Go, oh, that's pretty cool. So he tends to want every SerDes he has to be a separate port. So we prefer one 400 gig port. You prefer 400 gig ports than one 400 gig port.
Yeah, I guess.
Because you can split that out differently, assuming you have proper good load balancing. On my notes here, which was sort of scattered around, on the power side, they're looking at 120 kilowatts plus per rack.
Yeah.
That's per rack.
That's I know, that's insane. I'm sorry. I failed to. That's just, yeah.
So it's a lot. There's a project, I think it's Meta and Microsoft, called Mount Diablo. So it's a disaggregated power supply, which is running on 400 volt DC, and it's hundreds of kilowatts up to a megawatt.
So
And then how do you cool these things? Right. The answer initially is it's really complicated liquid cooling.
Yeah. So the 3 Mile Island thing is a perfect example of somebody made a funny joke or a meme.
That's really big.
I know. Like, I don't think people understand the scale of what we're talking about here. Somebody made a great meme about like we're burning down the Amazon rainforest so that somebody could get a picture of a woman with 3 breasts or something from Dowdy.
A hedgehog playing chess.
Yeah, exactly. Whatever.
That's the
right?
PG one.
And in this particular case, we're reopening the Harrisburg 3 Mile Island reactor for this.
Yeah, it's nuts, man. This is going to be what makes nuclear power like actually accepted in America. This is going to be
probably, but it's also going to be nuclear power next to the DC because the grid is not going to cover it.
Yep, you got it.
So where was I? So another one of the 12 networking truths is one size never fits all.
Very true.
And so it was interesting listening to our 3 guest speakers. 3 keynote speakers, which are Google and Meta and Microsoft. And they had some things in common. They also had a lot of things differently. I mentioned earlier the way Google builds a network, which is called the Jupyter architecture, is really quite different. Yeah. And part of it's because that's where they started. And also, I think they were building their TPU chips a long time before anyone else. So, if they look at scale out, they don't like latency jitter. They don't really care about latency so much, but they don't like jitter.
Oh yeah, okay. They don't like essentially variable latency. Yeah. I'm following.
And if you got full load balancing, lots of skinny links, then they reduce levels. Now the scale up network, they have their own thing called OCI, which I don't know that much about. They say it's 10 times faster, it's lossless, very low latency, And they're actually still bigger than other networks because they change them with this OCS thing. If we look at Meta, the scale-up networks are tens to hundreds of nodes, and the scale-out is 10K to 100K nodes.
That's a hell of a scale-out.
Right. But I mean, it's just the thing, right? One thing is, are you inside one of those big NVIDIA X or next to it?
Yep.
The other is, are you the full data set?
Yeah. Like the swarm way of doing things, right? Like lots of little compute.
Yeah. And then you get, scale out is where Ultra Ethernet Consortia fits and where Ethernet natively fits. Scale up is likely to be NVLink or this new thing called UA Link, which got announced like today. So this is another consortia.
Oh, wow.
Which is everyone but NVIDIA, because you know what?
No, but yeah, I mean, it's very clear why. They want to build their own shovels. They don't have to buy the shovel, right?
Well, actually, they just want to be able to buy shovels from more than one person.
There you
go. So if it's talking about what was most important to these guys, the first thing it got to was sort of resilience and reliability. I have some links about this, but basically clusters are so big that your failures are happening frequently, in order of minutes.
Oh, because you have hundreds or thousands of nodes. It's guaranteed that something's going to break somewhere.
Right.
So there's a link we can put in from some guys at Semi-Analysis, and they basically have a note about if you're building a cluster of 100,000 H100 systems. And you go, yeah, that's a lot. Now, the network isn't the biggest problem here. The biggest problem is somewhere else, but we're part of it. So the packet errors will only happen once in my lifetime. Yeah, there's a lot of lifetimes there.
Oh yeah. You were dealing with the economy of scale in all cases there. Packets, number of links, number of nodes. Just multiply it all out.
And so part of what these guys are looking for is as much information as we can give them about when things are going bad. So traditionally, we probably would have just given you packet losses. Now we're going to want to be going and doing it per lane, per symbol error, everything else they can do to figure out whether things are going to be okay. Because unplanned outages are very bad.
Oh, yeah, absolutely.
And how bad it is sort of depends on structure, because some people checkpoint really rapidly and some people don't. And so the real question becomes is when you have a link failure or you have a node failure, right, how much do you lose?
Yeah, especially if it hadn't, we were just talking about how they have to do a certain amount of computations, then check in, sync, and do all of that. So you're constantly essentially losing data to some degree, right? It's like an acceptable loss to be losing nodes.
The other one that I read recently and posted out was that they're blowing through the life of the GPUs really rapidly. I
saw that.
It's like, okay, so if your GPUs are going to fail after 3 years, I mean, that's interesting.
Yeah, I read that article too. It's crazy.
So just to call back to the point you made earlier about this kind of focus on I'm going to call it absolute optimal productivity, like no idling at all, right? Anything that's available should be consumed.
So yes, but what you also see is people end up they'll have some number of clusters sitting there idle so they can swap them in when another cluster fails.
Well, that's where I was going. So if I think about, I mean, this is a new thing, right? People, have been, if we think about, WAN circuits and things like that, the scale is new, right? But people feel like, I have two circuits at my site, I want to use both of them. Why is one sitting idle the whole time, right? So, but I'm wondering how much does this increase the amount of failures in a shorter amount of time because the resources are facing a higher level of constraint?
So the article we looked at basically suggested that since they're running full bore all the time as fast as possible and worth it as possible, the lifetime sort of stinks. And someone else made the point that, yes, we've seen this in Bitcoin mining.
Yeah, I mean, so the actual computation on a GPU bit, that's not new, right? That we've done it with Bitcoin for years, and those have been well known to be. They'll build Bitcoin farms, like what's that guy on Twitter? Adrian Kentrell that does the training for AWS. He was posting all the time about his Bitcoin farm stuff, like always having node failures and stuff. It was like every single day, man. And so that part's not new.
So this is like if you get your home computer and you overclock it, right? It's probably going to be a little flaky. And
that's known, that overclocking is known to lower the lifespan of your of your processor as well. I mean, you're cooking the hardware. Like that's just straight up. You're pumping it full of electricity.
I think at a GPU level, it makes perfect sense. I'm more speaking to how does it affect the network? If you want the network also running in that same capacity.
So I think this is where it gets complicated. So one way says these things cost so much, they've got to be running 100% of the time. But then you go, okay, so when I have a failure, what happens next, right? There's a whole bunch of stuff that seems to be about, certain numbers of things in a pod work better than certain others, depending on how your connectivity is. So you end up having to have groups of spares, so that when there is a failure, and they'll be running warm spares, so that when there is a failure, you can swap over with the least interaction with everyone else. But of course, this is a fun problem because if I bought all this expensive stuff, so we're going to get back to it is the n plus something failures, and how many do you have, and how many do you have standing by, and how long is the failure? So we've seen all this stuff, but again, the scale is just enormous.
It's crazy. I just thought about this, and I wonder if I'm sure somebody smarter than me has already thought of it, and they're trying to figure it out. But think about the supply chain of this, right? Like if you're buying 100,000 GPUs, you're probably like buying an entire run like of GPUs from Taiwan or something, or wherever the hell they're coming from. And they're all probably going to fail at about the same time. Like their lifespan is about the same.
I'm not sure how that works out. It does seem that, again, what I'm reading is that getting hold of these things is hard. Some of it depends on who you are, what your connection is. I think I read something the other day, which is Dell is becoming more loved by NVIDIA because I think they'll be able to deliver at scale.
Okay.
But there's probably enough mix-up between where they're going. I think when you buy 100,000, they don't all show up as one big.
Oh, yeah. Nobody. I couldn't even imagine the truck that would show up with that, right?
So if you're actually getting them as part of, the NVIDIA big racks or something else, I'm sure there's a bunch of mixing in there.
Yeah, but I mean, but we're not talking about onesie twosies, though. I mean, if you buy 100,000 from NVIDIA, you're probably having a few hundred show up. I guess I'm saying, and you're right, split over that many nodes, you probably don't really notice, but at some point, you're going to get into some kind of cycle of supply where you're probably burning through a decent amount of nodes at the same time.
Sure, and I think that's probably true. But if the reality is that they have a 3-year lifetime anyway, that's not that
true.
long.
It's just constant swapping all the time at that scale, right?
So this is like the Sydney Harbour Bridge, right? You start paying at one end, by the time you get to the other end, you start again. So everyone cares about power, and they really care about increasing work per watt. They're going to deliver as much power and cooling into a rack as they possibly can. And the question is what can you get out of that? And again, the networking part is close to the loss in the noise here. But if it's a watt they spend on networking, they can't spend it on the other stuff.
Yep. But they can't not spend the money, right? You got to have the network. It's not like they can't spend it,
right? But your goal is to make it as small as possible. Again, it's work per watt, and this gets really interesting because if they want to run any reasonable distances for some of these links, they have to run optics, and optics is really expensive.
Oh my God, yes.
And then you go, well, I want to run copper over 20 meters. It's like, but I don't want to pay for FEC. It's like, yeah, we can't do that. And so, a whole lot of places here, physics is hard. So it's changing so much. The scale is so huge. I don't think it's going to stop anytime soon.
And I didn't necessarily want to get there yet, but it begs the question, really. Just the whole thing we just talked about just truly begs the question, the unasked question, which is, if we spent this much money for this much workload, like, where is the ROI? Like, what are we getting out of it?
I have been wondering that myself. Okay, so this is a question that should not be asked, of course, because the answer is it's just wonderful and we need it. But I sort of wonder about level 3 when they put all the fiber in the ground and went bankrupt. All that fiber is being very useful at the minute to these people who want fibers. But I'm not sure that I see the ROI here. I understand we must do it because we have to. But so for the time being, let's put that one aside.
Yeah.
Because that's a problem we can't solve here. That's a problem for the business people. But what we have at the minute is we have this problem that our customers want us to solve yesterday. and they're really hard, right? The engineering. So one of the presentations I was listening to, the engineer presenting it was talking about sitting in connectors, and just where the metal wipes and doesn't quite finish, there's a tiny piece there, right, which becomes a stub in the transmission from the transmission line. And so you can have stubs where there's, like a millimeter of metal. You go, oh, this is getting pretty interesting. So the physics is hard.
I mean, yeah, I guess it makes sense. Like, imagine having to have essentially perfection to get like this level of low latency without any problem. Like, from a machining perspective, from a fabrication perspective.
And so then you go down to so we want to reduce load, and you see a whole lot of stuff with people building flyover cables, right? Because flyover cables are better than PCBs, but they're also sort of complicated. Then it's like, how close can the flyover cable drop onto the chip? We've seen a whole lot of conversations about co-packaged optics, but that doesn't seem to be taking off. So you're left with SerDes coming out of chips, and getting it to the other end is hard. If you go way at the top end of systems, you see people building cable backplanes, right? Because the results are just better than running on a PCB, but they're mechanically really complex.
Okay. To be fair, I haven't seen this, so I'm having trouble.
Okay, so go back to the pictures. Remember when the telephone exchanges, all these people plugging stuff in? Sure. Imagine that.
It's that, basically. Okay. Excellent.
Yeah, it's lots of cables running everywhere, which is a technical solution, but I'm not sure it's a solution you can build by the tens of thousands. Because not only is this hard, they want want these things in hundreds of thousands to millions.
So I remember a year ago when we had this conversation, we did have...
Your memory is much better than mine, Chris. I got to tell you.
You got to go back and watch your episode after this.
Yeah. We did have this conversation.
I try to avoid watching myself. I can never handle it.
I recall that we had this conversation about, these purpose-built networks, right? Building them for a certain length of time for training a model, right? When you need the utmost performance in that scale. So, I mean, I get where the hyperscalers and, Google, Meta, and Microsoft all need that capability. But are you having conversations about these purpose-built networks for the purposes of training at the enterprise level? And how do you make that modular and consumable from that level?
So I'm not on that side of Cisco house. In my head, this looks like specialized networks. And I did read something earlier today about how much bigger Microsoft's thing was than what's in Los Alamos. So my running theory is the original model training is going to be have to do the web scalers. My guess is adjusting a model is probably something you read from Amazon.
Like fine tuning, you mean?
There's a whole lot of groups out there who are off building AI data centers with a plan to rent them to the web scalers. So my guess is it becomes a thing you can go rent. I think for most people, that's the only way you could do it because you couldn't get them busy.
I think we thought the same thing. Honestly, this is triggering my memory now as well. And I think we had the same idea a year ago and having now put a year between back then and now and seeing the way things are going, I think that's still pretty safe. I think it's still a pretty safe bet.
It gets a little interesting for you guys know what FedRAMP is?
Yeah.
Okay. It gets a little interesting for the classified cloud, but I think the web scalers have already solved this. They're already selling that.
Actually, it just occurred to me, our listeners may not be familiar with FedRAMP. It probably would be useful to spend the 10 seconds. If you...
I would say FedRAMP is the requirements you have to meet to sell into classified and federal.
That's right.
And so when the cloud stuff first came up, it's like, cool, there's this cloud thing out here, we can't use it. But if I recall correctly, both AWS and Azure have now got a FedRAMP certified cloud service.
That's correct. I mean, even where we work, we have to deal with this stuff as well.
And if you get back to the conversation about Microsoft buying the power from 3 Mile Island for 20 years, I'm not seeing that in an enterprise DC.
Oh, no way, right? Like at best, I think it's closer to what you said, right? Like the enterprises aren't going to build like a true scalable data center that's going to do AI work. Like they could probably have something small for like fine tuning a model they already have access to or something like that, or RAG or something
we're already
like
having
this.
conversations about whether or not it's even worth it to make your own model, right? Where's the ROI on that? If we're talking about building the infrastructure, fuck no. There's no.
So again, this goes back to, okay, so you want to do generative AI and you say it's wonderful, and then you go and ask the CFO for the money. He looks at you and says, really? So my guess is that, we're already seeing companies will not run against the public model. They have their own copy locally because they don't want stuff to leak. I think Samsung was probably the worst one for that.
Oh, yeah, for sure.
I think the real question is training models doesn't make money. Inferencing makes money.
Exactly.
And then the question is where is the inferencing going to run? And so I don't know anywhere near enough about this to be correct, but I sort of see it seems like inferencing is going to become part of a standard data center workload.
Yeah. So, one thing that I'm doing a presentation at AWS reInvent, and one of the things we're talking about, one of the things I'm presenting about is like this idea of a disaggregated RAG, where you can keep your data source completely on-prem and just send vector data into a database in the cloud, right? For enrichment purposes, like for the same reason you just talked about, which is that you don't want to put your data, you don't want to give your data to the cloud or put it in the model.
I think that becomes a little interesting because, so that's why you've seen people shuffle stuff around for data sovereignty stuff. Yeah. But I think people would have to go and take a look and say, what's the risk reward of putting it in both places? But I was more going, okay, so you have a model you need. Whoopie-doo, congratulations, very well done. Then you have to actually provide something useful out of it, which means you're inferencing. I don't see how you split that from the standard data center workload. It's going to be everywhere.
Right.
So then, again, in my head, we used to have specialized networks for everything. There'd be a storage network, or this network, or that network.
Yeah, sure.
Now we've sort of gone hyper-converged. So if I look out a few years, what does the standard data center workload look like, right? Does it have a bunch of normal servers over here and an inferencing group over there? Right. Is it scattered across the middle? I don't know the answer, but my guess is ultimately the web scalers are very economically rational. They're going to do whatever is the cheapest.
Sure. I think that's definitely true.
I would think they also build these things to be insanely modular, right? You want to be able to just throw things in, throw things out. And I feel like the only way you're really going to have uniformity is if you have dedicated pods essentially that are doing the same task. So I would see all the inferencing falling in one spot and all the training falling in a different spot.
So the counter argument would be if training is somewhere over there, but when you're doing stuff and you're inferencing and doing other web workload and storage and everything else, inside that part of the network, do I have like 3 separate components, or is it all one thing with everyone being able to do some of it? Do I have like 100 servers over there doing compute and 100 GPUs over there doing inferencing and go backwards and forwards, or do I put them all inside the same rack?
Yeah, that's a really classic. It's funny how the more things change, the more they say the same, right? Like, because that's a very classic question, right? In terms of purpose building your workloads.
Rule 11.
Exactly. I was just thinking of that one, actually.
For those who aren't following along, Rule 11 of the 12 networking truths is every alternate will be proposed again with a different name, a different presentation, regardless of whether it works.
Yep.
So I think the answer is there is so much happening. I think the problem we actually have is there's so much information it's hard to consume. At risk of a plug for a friend, I've been reading some stuff from a group called Semi-Analysis. They're a analyst firm, but a little different. So they have a feed you can subscribe to in Substack. Now, about, I don't know, it's like half you can see and half is paid. But the half I could see was enough to persuade me to actually pay for it. They got a lot of cool stuff out there. And so that's somewhere I suggest people go because they've done a bunch of looking at it. Now, it's not a light read, but it's hard to know what you do when you look at Google and Meta and Microsoft and all these other guys because they're all different. They've all got lots of stuff.
Yeah, that's a lot.
As I said, the other thing is people people should go take a look at all the stuff from OCP because the slides and the video are there. And, for me, if just the slides isn't good enough, you really need to see the explanation on the way through. But it's really complicated, it's expensive, and it's really hard. And the problem we're going to have is how do we avoid building everything?
Yeah. Yeah, no, and this is honestly, I feel like this show is going to be a heavy lift for a lot of people, myself included. So I want to make sure we're going to get all the links, and as Peter's warned, I'm sure a lot of this will not be a light read. But this is going to be, whether we like it or not, this is probably going to be a big part of networking, both in the cloud and out of the cloud. And
it's going to be huge,
so, yeah,
in subset of the cloud. And right now, that subset of the cloud is consuming everything else. But as far as I can figure out, it's also being built in a very scalable fashion, in which case they build it once, they build it a lot of times. So I don't know what percentage of people will actually ever get to play with this stuff. I think it's going to be, you're going to have to be fairly high up in those organizations to get there. I think for the rest of us, it's like watching Formula One. It's a very cool thing. I'd like to understand it. I'm not sure I'll ever get to build it.
Yeah, right.
Yeah, I might be able to consume it or pay somebody to give me a ride in it, but...
Now, I think the question you actually get to is what out of this comes back to a more broad market? Because this market at the minute is quite narrow, but extremely deep. Now, what out of this comes back to a more broad market? I don't think we know yet.
Yeah, I think that's fair.
Yeah.
Oh man, we could just keep going on this.
And I do have to warn you: if you stay here, I will just keep talking.
All right. Well, that's probably good. Good as reason as any to go ahead and wrap it up. This has been such a good episode. I'm actually going to be chewing on these links for a while. I'll make sure we get them on the show notes.
So Tim, maybe what you do is we let it simmer for a while, and maybe we come back like in a few months, and maybe do here's what we heard from people. Can we try and figure it out together?
We'll just do a quarterly update with Peter.
Yeah, we're just gonna have to have Peter on it for a quarterly update. We can't wait another year. This shit's moving too fast, right? So we would definitely agree. This has been awesome. Oh, go ahead.
No, it's okay. I was just going to keep talking.
This has been awesome. I'm really glad we were able to get you back on. We will definitely have you back on earlier than a year from now. There's so much more to talk about. We'll get all the stuff in the show notes, and thanks for joining us tonight. Any closing thoughts, Chris?
No, I think it's been good. We wanted to keep it as just kind of a conversation rather than.
I don't do formal stuff, right? I really don't.
Right.
So I think we did good on that front, and it's interesting to hear how things changed. Obviously, we need to do this in a few months rather than 12 months. So we'll make sure to do that. But I think it's good.
I mean, I think the other thing is to try and figure out what sorts of people you want on, because I mean, I like being on, but. I know much.
We've got some ideas.
Yeah, much out there.
We were actually thinking about this before, so don't worry. We've got a follow up.
We'll reach out because I'm sure you got connections for people that could come on here and just blow everybody's mind even more. So yeah, definitely. Okay, so so this is Cables to Clouds podcast. Thanks for listening. Thanks for watching. If you're on YouTube. If you're not on YouTube, you should go on YouTube and subscribe to us. Buy our breakfast cereal. Sign my birthday card. My birthday is next week. I'll
send it.
Where is your coffee mug?
Not on my desk. It's night here, and I don't usually drink coffee at night.
This is the problem. Coffee.
There you go. We do actually have a Cables to Clouds coffee mug, so buy our coffee mug if you would.
Yes,
not you personally. I just mean our listeners. But we will see you next time on another episode.
Hi everyone, it's Chris, and this has been the Cables to Clouds podcast. Thanks for tuning in today. If you enjoyed our show, please subscribe to us in your favorite podcatcher, as well as subscribe and turn on notifications for our YouTube channel to be notified of all our new episodes. Follow us on socials at Cables to Clouds. You can also visit our website for all of the show notes at cablestoclouds.com. Thanks again for listening, and see you next time.